We derive a differential equation for force equilibrium in this video. So it's a differential equation of force equilibrium. In a previous couple of videos, we discussed that the equilibrium or static equilibrium of force is given by three equations, such as summation of forces in x direction is 0 and summation of forces in y direction is 0. These are the equations for force equilibrium. And we have also another equilibrium for static equilibrium of a body, which is summation of moments about z is equal to 0. But we are only concerned about the force equilibrium equations in this video here. So let's consider a body of not unit volume. We are considering a body of dx in x direction, dx length in x direction, and dy in y direction, and of unit length in z direction. Because we consider a two-dimensional body, we only take dx and dy, and the third dimension is taken as unity. Now let's assume the stresses acting in the body as sigma x along x-axis, and if it's acting in this phase is sigma x, then you will have a rate of change across the length of dx, and then you will have a different stress at this plane. So that will be sigma x plus a rate of change of sigma x, that is tau by tau x of sigma x times the length, that is dx. So that will be the stress in this phase. Similarly, you have a sigma y here, and similar to this you have a sigma y plus a rate of change of sigma y times length, that is dy, acting in this plane, which is dx times 1. The area corresponding to this stress will be this area, which is dx times 1. So this area is dx times 1, and this the area corresponding to this stress and this stress will be similar to this area, and as you can see, that area is dy times 1. So the two areas in question in this case is dx times 1, which represents the top edge, top side, and the bottom side, and also you have the right side, and on the left side you have dy times 1, and the volume of the body is dx times dy times 1. Now you have a shear force, shear stress acting here. Let's take it as tau x y, and therefore you will have a corresponding shear stress in this plane as well, and you can write it as tau xy plus a rate of change of tau xy times dx. And similarly you have a tau yx here, and therefore you will have a tau yx plus a rate of change of tau yx times dy acting on this plane, which again is dx times 1. The area of the plane is dx times 1 and dy times 1. Now for equilibrium, you should have the force corresponding to this stress plus the force corresponding to this stress plus the force corresponding to this stress plus the force corresponding to this stress should be equal to 0, because those are the forces acting along x direction. So this force plus this force plus this force plus this force should be equal to 0. Let's try if we can write that equation there. So for force equilibrium in x direction, we should have summation of forces in x direction equal to 0, and that will give you, we take this as a positive force because that is acting along the positive x direction, and let's take this as a negative force. And as you can see, this is in the positive x direction, this stress also is in the positive x direction, and this one is in the negative x direction. So you have sigma x plus rate of change of sigma x dx, which is this stress, and the corresponding area is dy times 1. So you get the force minus the force corresponding to this stress, which is sigma x times dy times 1, plus you have this stress here. You have this stress which is acting in the positive x direction, so that is tau yx plus rate of change of tau yx times dy times the area, which is dx times 1, minus you also have the force corresponding to this stress, which is tau yx times this area, which is again dx times 1. Tau yx times dx times 1. Now we have one more force here, which is any body force or any inertia force or any electromagnetic force in this field. We just take it as along the x direction, we just take it as x per unit volume, and the ones in y direction we take it as y per unit volume, and therefore the force, corresponding force to x will be x times dx dy 1, because this is the volume of the body, and that corresponding to y will be y times dy times dx times 1. So any body force or any inertia force or electromagnetic force whatsoever in that field is considered as x per unit volume. So you have, along with these forces, you have plus x times dx dy times 1 is equal to 0 for the force equilibrium along x-axis. Now you can see you have a negative dx into sigma x into dy times 1 here, and you have a positive sigma x dy times 1 here. So this term will be cancelled, this term also will be cancelled, and similarly you have a minus tau yx times dx times 1 here, and also you have a positive tau yx times dx times 1 here. So that term also will be cancelled, this term also will be cancelled, and therefore you will have tau by tau x times sigma x times dx dy times 1, which is this term here, plus tau by tau y tau yx times dy times dx times 1, which is this term here, plus x times dx times dy times 1 is equal to 0. And as you can see, these are common terms. Dx times dy times 1 are 3 common terms, and therefore you can cancel that as well. So you have tau by tau x sigma x plus tau by tau y tau yx plus x is equal to 0, which is the two-dimensional case of our differential equation for force equilibrium along x direction. So that's a 2D case. And if you follow the same analogy, you can write the force equilibrium in y direction as well. Just from this, just change the x's to y's, and you will get tau by tau y of sigma y plus tau by tau x of tau x y plus y is equal to 0. And that is your force equilibrium in y direction for the 2D case. And following the same conditions, you can write the force equilibrium for 3 dimension as well. But remember, when you consider the 3-dimensional case, you will have a dz here instead of the 1. So you have a dx, dy and dz. So following the previous assumptions, we can write for 3 dimension that dou by dou x of sigma x plus dou by dou y tau yx plus dou by dou z tau zx plus x is equal to 0, and that's equation 1, which is for force equilibrium in x direction. And also you will have dou by dou y of sigma y plus dou by dou z tau zy plus dou by dou x tau xy plus y equal to 0 for force equilibrium in y direction. And you also have force equilibrium in z direction as dou by dou z sigma z plus dou by dou x tau x z plus dou by dou y tau y z plus z equal to 0. So these 3 conditions are the force equilibrium along x, y and z direction, and that is the cases for 3-dimensional force analysis. And these 2 are the same cases for force equilibrium in x and y direction, and they are only for the 2D cases. Even though this seems to be a bit confusing, if you understand this concept, it will be very useful in heat transfer, mass transfer and fluid dynamics as well, because in most of these cases the flow of heat also is analyzed using a similar method, and you also use the fluid flow analysis. The same method is used in fluid flow analysis as well. So what you have is a stress here, and a corresponding stress is calculated from the rate of change of this stress. So sigma x here, sigma x plus rate of change of sigma x times the length, that is the stress here. You have a sigma y here, and here you have sigma y plus rate of change of sigma y times length. You have a tau xy here, and you have a tau xy plus rate of change of tau xy times length here, and you have a tau yx here, and you have a tau yx plus rate of change of tau yx times the length here. So for force equilibrium, the force corresponding to this stress and this one and this one and this one should be 0. And if you consider a force equilibrium in y direction, you should consider the forces corresponding to sigma y and this stress and this stress and also this stress, and summation of all these forces should be equal to 0, and that's what we derived through this equation here. And following on from the 2-dimensional cases, we can also write the three-dimensional equations using the same method. You don't have to derive the entire equation, but you can just write by understanding x, y, the positions of x, y, and z.